Hey guys, my name is IBM and today I'm taking you to October November. I'm taking you through October November 2024 papers, and this is paper 4.2. This is A-level structured questions. Do not forget to visit our website www.caieresourcemaster.com for the resource for several resources that you can find there. Just to remind you, you can visit the website, and when you visit the website, you can find resources that you want. This is how the website looks like. And you can go to any subject. There are around 8 subjects here. Most of them are still developing resources, but for now, I think physics has most of the resources. And in a short time, most of these subjects will have resources. But at least I know all A-level papers are present. All past papers in these subjects are present. Well, they have been uploaded and they are free. Just try to make our website busy so that it can do other things for us. So, of course, other resources like the tutorials, the topical questions, they may not be free, but I know the past papers are totally free. Like I said, when you purchase a resource on that website using PayPal, uh, the, the website will look like this after completing the purchase, and then you just click on download and download your document. Okay, so let's go straight to question number one without wasting time. I'll go straight to question number one. I want to try as much as possible to use less time in this paper than it was in the previous paper. So a metal wheel consists of an axle A, 8 spokes, and a rim as shown in the figure. Point X on the rim is on the rim at the end of one of the spokes. The rim has a radius of 0.85 meters. The wheel is rotating clockwise. The wheel is rotating in this direction clockwise with an angular speed of 140 radians per second. For point X, determine the speed. So because they have given us the angular velocity, we know that velocity v, the linear speed v, is going to be equal to omega times r. And this is going to be equal to the angular velocity, which is 140. The angular velocity is 140 radians per second times the radius, which is 0.85. And when you press our calculator, 140 times 0.85, that's 119, or which is approximately 120. So I'll write about 120 meters per second. Then the centripetal acceleration. Remember, we know that our centripetal force is equal to mass times centripetal acceleration. And centripetal force is equal to mv squared over r. When you compare the two equations, it means that the centripetal acceleration is going to be equal to v squared over r. So since v squared is 119 squared, divided by r, where r is the radius, that is 0.85. So I have 119 squared divided by 0.85. So that is 1666. So this is 16660. Of course, this is in meters per second squared, which is approximately 1.7 times 10 to the power of 4. So this is 1.7 times 10 to the power of 4 meters per second. There is a uniform magnetic field of flux density 0.18. So this is going to be B. It is into the plane of the page. State Lenz's law. Of course, Lenz's law deals with the direction of the induced EMF. So we shall say, the law states that the direction of the induced EMF is such as to produce effects that cause the change that caused it. So we shall say the direction of the induced EMF, the direction of the induced EMF is such as to produce effects that oppose the change that caused it. The direction of the induced EMF is such as to produce effects that oppose the change that caused it. Show that the time taken for point X to complete one revolution is 45 milliseconds. So we want to find the period. So we know that period equals to 2 pi divided by omega. And this is going to be 2 pi divided by omega, which was 140. So divide by 140. And then from my calculator, 2 pi divided by 140. So that is 0.04488. 0.04488. 0.04488. That is seconds. To introduce milli, we divide by 10 to the power of minus 3. So this is 0.04488 divided by 10 to the power of 3, 10 to the power of minus 3. To make it milliseconds, we divide to make it milliseconds. So divide this by 1 exponent minus 3. So to bring a prefix, we divide by its value, so it becomes 44.88 milliseconds, which is approximately 45 milliseconds to two significant figures. Normally, whenever the equation is shown that, it's always better to write the previous answer, which rounds off to what is given, and especially if it's not exact. Capture the magnetic flux cut by the spoke AX during one revolution of the wheel. Magnetic flux. Of course, we know that flux equals to AB or BA, where B is, of course, the magnetic flux density and A is the area. So the area which is going to be swept through is going to be a circular area. So the area is equal to pi r squared. So the magnetic flux is going to be equal to B, which was, I think B was 0.1 Tesla, 18, times the area, which is going to be pi. The radius through which the bicycle spoke sweeps is 0.85, but this is squared. So using my calculator, 0.18 times pi times 0.85 squared. So this is 0.409. Or it can be approximately 0.41. Just avoid writing answers to one significant figure. There should be a minimum of two significant figures. The units of magnetic flux that you mentioned is the Weber, or you can find area is meters squared and B is Tesla. So it can also be Tesla meters squared. But I will take the Weber. So this is going to be 0.41. The units is the Weber. Then determine the magnitude of the electromotive force induced across the bicycle spoke. That is the induced EMF. So the induced EMF, according to Faraday's law, is the rate of change of the magnetic flux. So it is the change in the flux by time. So that is the rate of change of magnetic flux. or you can just, it is changing, it is flux over time. So this is going to be equal to, the change in flux is going to be 0.41, assuming it changes from 0 to that, or it changes from this to 0. Then this is going to be divided by the time. For one revolution, this is going to be 0.45 milliseconds, which is 45 times 10 to the power of minus 3 in one revolution. So I'll just divide this 0.41 divided by 45 exponent minus 3. So that is 9.1 recurring. So this is approximately, of course, this is EMF in joule in volts, so it's approximately 9.1 volts to one significant figure. Use Lenz's law to explain whether the potential is higher at end A or end X of the spoke. Let's see. Remember, we're using Lenz's law to find out whether the potential is higher at end A, this is end A, or it is higher at end X. Now note that the wheel is rotating clockwise. The wheel is rotating clockwise. So at this point, remember they said the magnetic field was, I think it was into the page. Let me check here. They said it is into the plane of the page. So the magnetic flux is into, the magnetic field is into the plane of the page. So the magnetic field here is into the plane of the page. And at point X, the wheel is just moving in that direction. So the direction of motion is in that direction. So which means the force is going to be vertically downwards according to the diagram. According to the rotation, the force at point X is vertically downwards. So we now have to pull out Fleming's left-hand rule. First of all, by Lenz's law, the force on the spoke must be opposing the motion. Because the motion is clockwise, the force is going to be anti-clockwise according to Lenz's law. If there was no Lenz's law, the motion is downwards, but because there's a magnetic field, the force is going to be in the opposite direction. So I'm going to change the direction of the force. Because motion is clockwise, the force is such as to oppose the motion. So at point X, the force is going to be in the opposite direction. That is the direction of the force because of the presence of the magnetic field. When we bring Fleming's left-hand rule with the thumb pointing upwards and the first finger pointing downwards, the thumb is pointing upwards. This is the thumb because the thumb points in the direction of the force. The first finger points in the direction of the magnetic field. So if you have your right hand, your left hand, your first finger must be pointing onto the paper which is on the table, and your thumb must be pointing upwards. And you notice that the force, the second finger is pointing in that direction. That is going to be the direction of the current. So the field is into the page, that is the first finger. The thumb is pointing upwards, that is the force. The second finger, which is the current, is pointing in that direction. So by Lenz's law, the force is upwards on the bicycle spoke. It must be anti-clockwise. And by Fleming's left-hand rule, the current is going to be from A to X. So X is, and if the current is from A to X, and the current is the flow of charge carriers, then it means X is going to be actually, by Fleming's left-hand rule, the current is going to be from A to X. So if I use Fleming's left-hand rule, the second finger or the current finger is actually going to be pointing towards the high potential, which would mean that X is going to be at a high potential. However, many of you who have understood this topic, you notice that the induced current is always easy to predict by Fleming's right-hand rule. And if I use Fleming's right-hand rule, first finger is pointing upwards, second finger is the thumb is pointing upwards, the second finger is pointing into the page, The thumb is upwards, the first finger is pointing into the page. You'll notice that the second finger, which shows induced current. For Fleming's left hand rule, the second finger shows induced current, and you notice that the second finger will point in that direction, which would mean that the current is actually flowing from X. The X is going to be at a high potential. Therefore, we are agreeing that X is actually at high potential. When I use the Fleming's left hand rule, the second finger points towards X. When I use Fleming's right hand rule, the second finger points towards A, which means because the second, we normally use the Fleming's right hand rule for the induced current, and the second finger points in the direction of flow of current, or the direction of flow of the induced current, then it means X is going to be at high potential. So I'll simply say by Lenz's law, the force on the spoke is going to be such as to oppose the change producing. So force on the spoke must be anticlockwise. And by Fleming's left hand rule, left hand rule, the current is from A to X. So the current is from A to X, and if the current is from A to X, because note that in this case the charge carriers are going to be the electrons, which could be moving from A to X, therefore X is going to be at a high potential. So X is at the high potential, or is at the higher potential. Okay. The Sun may be considered as a uniform sphere with a mass of 1.99 times 10 to the power of 30 kilograms and the surface temperature of 5780 Kelvin. A probe with a mass of 2.63 kilograms moves in a straight line towards the Sun. When it is at a distance x from the center of the Sun, the probe measures the gravitational field strength G due to the Sun and the radiant flux intensity F of radiation from the Sun. Define gravitational field. Of course, gravitational field can also be defined in the same way we would define gravitational field strength, because a field is a region of space where a force is experienced. So the gravitational field can be defined as a region of space where a unit mass experiences a force, or you can define it as the force, because G is going to be equal to force over a unit mass. So this can be defined as the force per unit mass. Or I can define it as a region of space where a unit test mass experiences a force. For the positron of the probe, where x is 1.47 times 10 to the power of 11 meters, calculate G. Of course, we know that gravitational field strength G is given as capital G, capital M over x squared. This is going to be 6.67 times 10 to the power of minus 11, then times 1.99 times 10 to the power of 30, that is the mass. Yes, that is the mass. Then we divide this by the radius, which is going to be 1.4. So the distance from the center, which is 1.47 times 10 to the power of 11. 6.67 exponent minus 11 times 1.99 exponent 30 divided by 1.47 exponent 11. So that is 9.03 times 10 to the power of, oh, this was squared. This is x squared. So just to divide again, because this is squared, so I'll say divide. Okay, let me just correct this. So that is 6.14 times 10 to the power of minus 3. Determine the gravitational potential energy of the probe. So we know that gravitational potential energy is negative capital G, capital M, small m divided by x. Now remember that here the minus is not optional, it is compulsory. So this is going to be minus 6.67 times 10 to the power of minus 11 times 1.99 times 10 to the power of 30 times, what was the mass? The probe was 2.63. So I'll say times 2.63 divided by x, that is the distance from the center, which is 1.47 times 10 to the power of 11. So 6.67 exponent minus 11 times 1.99 exponent 30 times 2.63 divided by 1.47 exponent 11. So that is 2.37 negative. So that is negative 2.37 times 10 to the power of, which power is that? 369, power 9. So this is going to be minus 2.37 times 10 to the power of 9. Show that for any particular value of x, the numerical value of g and f are related by this equation here. Okay, so earlier on we have already mentioned that g equals to capital G m over x squared. And of course we know that f, what is f? What is f? F is the radiant flux intensity. Of course, we know the formula for radiant flux intensity. Radiant flux intensity is equal to the luminosity divided by 4 pi. Then D, because here they gave us, since it is just on the surface, then instead of D, I'll put there x squared. That is the distance from the point, from the center to the surface. So the radiant flux intensity is going to be 4 pi x squared. We are used to F being equal to 4L over 4 pi d squared. But this time d is the same as x. So I could make x squared the subject in both cases and substitute, or I could make 1 over x squared the subject. So here I have that x squared is equal to g m over g, and at the same time x squared is equal to L over 4 pi times f. So this means that capital G capital M over G is the same as L over 4 pi f. We just cross multiply. So this means we have capital G, capital M times 4 pi f equaling to G times L. So making G the subject, so G is going to be equal to 4 pi f times Gm divided by L. So hence, we have already shown that G equals to 4 pi capital G capital M over L times F as required. The figure 2.1 shows the variation of G with F. Determine a value for the luminosity L of the sun. Give a unit with your answer. So let's find the relationship. It is a graph of G against F. From that previous equation, we saw that G is equal to 4 pi capital G capital M divided by L then times F, which means the gradient, when you compare this with y equals to mx, there is no y-intercept anyway. So you see that this is the gradient. So that is the gradient. If we have a graph of G against F, that is going to be equal to the gradient. Alternatively, I can just make a simple substitution. I will not use the gradient. I can simply say L luminosity is equal to, because the graph goes through 0, 0, it's the same thing. So the luminosity is going to be 4 pi capital G, capital M, capital F divided by small letter g. So this is 4 pi, then times 6.67 times 10 to the power of minus 11. The mass was, I think, 1.99 times 10 to the power of 30. Then F, I'm going to choose a value for F here, which is convenient for me. This one is hard for me to estimate. I will not use that one. Let me use this part here, where this is 1 against this value is, I think this is going to be 4.4. That is easier for us to estimate. So this is going to be, the value of F is going to be 1.0 times 10 to the power of 3 divided by the corresponding value of G is 4.4 times 10 to the power of minus 3. You can use any other value, any other pair of values. So we have 4 pi times 4 pi into brackets 6.67 exponent minus 11, open another bracket, 1.99 exponent 30, 1.0 exponent 3, then divide by 4.4 exponent minus 3. So that is 3.79 times 10 to the power of 26 watts. I think we are familiar with that number from astrophysics and cosmology. So L is going to be 3.79 times 10 to the power of 26, and the units is of course watts. Luminosity is total radiant power emitted by a star, so the units is watts. Use your answer in serum and 2 to determine the radius r of the sun. We also know that luminosity is 4 pi sigma r squared t to the power of, I think this is given the list of formula. So the radius is going to be the square root of L divided by 4 pi sigma t to the power of 4. Making a substitution, this is going to be the square root of 3.79 times 10 to the power of 26 divided by 4 pi. Sigma is given the list of constants, I think it is 5.67 times 10 to the power of minus 8. Then I think that is Boltzmann's constant. I know that is Stefan Boltzmann's constant. Then this is times the temperature was given as, I think it is 57 something, 578 Kelvin. So I'll simply say times 5780 raised to the power of 4. Okay, I'll simplify the denominator first. So that is 4 pi times 5.67 exponent minus 8 times 4780 power, no, where's the button for power? I'm not used to this calculator. So this is 5780 raised to the power of 4. Okay. So that is 7.9. So then I will set the I'll open bracket 3.79 exponent 26 divided by the answer. Then I find the square root of the answer, and it is 6.9 times 10 to the power of 3678. So it is 6.9 times 10 to the power of 8. So the radius is 6.9 times 10 to the power of 8 meters. Define specific latent heat. Of course, specific, this is per unit mass, 1 kilogram. Latent, there is change in state. The state changes, change in state, but no change in temperature. No change in temperature. Okay, so I will simply say that this is the thermal energy. Thermal energy needed to cause change of state of 1 kilogram of a substance. 1 kilogram of a substance, to change the state of 1 kilogram of a substance without changing temperature, or at a constant temperature. At a constant temperature. So whenever it is latent heat, there is no change in temperature, but there is a change of state. If we mention specific, then that is 1 kilogram. That amount of heat required to change the state of a substance, especially mass 1 kilogram, at a constant temperature. It can be from liquid to solid, solid to liquid, whichever. But as long as it's 1 kilogram of a substance at a constant temperature. A dish containing 7.2 times 10 to the power of minus 5 meters cubed of a substance rests on a laboratory bench. The substance is initially a liquid. Initially liquid of density 710 kilograms per meters cubed. Atmospheric pressure is 1.0 times 10 to the power of 5 pascals. The liquid is heated at its boiling point. The liquid is heated at its boiling point that it completely vaporizes. So it's like volume increases. The increase in the internal energy of the substance during this process is 17.6 kilojoules. The increase. The final volume of the vapor is 0.017 meters cubed. So volume has increased. Show that the magnitude of the work done on the substance when it vaporizes is 1.7 kilojoules. The final volume is this. There's an increase in volume. So work done equals to pressure times change in volume. This work done is going to be negative because the volume increases. So this is going to be the pressure, that is 1.0 times 10 to the power of 5 pascals times. Show that the magnitude of the work done on the substance when it vaporizes is that the final volume of the vapor is 0.017. So a dish containing 7.2 times 10 to the power of minus 5 meters cubed of a substance rests on a laboratory bench. So it means the substance is initially a liquid. So initially it means the initial volume of the vapor is 0. So the final volume is this. Because it was initially liquid, it was not initially vapor. So this is going to be 0.017 minus 0. So this is going to give us so we have 1 exponent 5 times 0.017. So that is 1700 joules, which is the same as 1.7 kilojoules. And I said this is going to be negative because volume increases. So in further calculation, we may need volume increases, so W is negative by convention. Use the information in B Roman 1 to calculate the thermal energy Q in kilojoules supplied to the substance to change it to vaporize. So we know that the change in internal energy or the increase in internal energy is going to be Q plus the work done. So the increase in internal energy is 17.6. This is going to be Q plus the work done is going to be negative 1.7. So that means Q is going to be 17.6 plus 1.7, which gives us, I think this is 3, that is 19. So that is 19.3 kilojoules. Use your answer in B Roman 2 to determine the value for the specific latent heat of vaporization. Of course, we know that for vaporization, Q is going to be mass times the latent heat of vaporization. And we know that the mass is equal to, I think mass is density times volume. The density was 710, I think. Density is 710. And the volume of the substance was 7.2 times 10 to the power of minus 5, I think. Yes. So that is the mass. Then it means the latent heat of vaporization is going to be Q divided by the mass, which is going to be, we have got Q as 19.3 kilojoules, so that is 19.3 times 10 to the power of 3 divided by 710 times 7.2 times 10 to the power of minus 5. Calculator, 19.3 exponent 3 divided by 710 times 7.2 exponent minus 5. So that is 377,543. So 377,543. So this one is actually joules per kilogram. Now the answer is required in kilojoules per kilogram. So that means I'm going to change this. Of course, I would have this is actually kilos, so this is going to be bringing in a kilo dividing by 1,000. So this is going to be 377.543 kilojoules per kilogram. And this is approximately 380 kilojoules per kilogram. So I'll write here 380 for simplicity. The substance in B has a specific latent heat of fusion, LF. Suggest and explain whether LF is likely to be less than, the same as, or greater than the answer in B. Of course, we are very much aware that the latent heat of vaporization is greater than the latent heat of fusion because of the large volume change involved during vaporization than fusion. So, because there's a large volume change during vaporization than fusion, it means there's a large intermolecular, there's a large change in, there's a large change in the spacing between the molecules during vaporization. Therefore, the potential energy Therefore, the potential energy involved during vaporization is higher than that during fusion. This, which means the internal energy for vaporization is higher than the internal energy for fusion. Therefore, the specific latent heat of fusion is going to be always smaller than the latent heat of vaporization. So we shall simply say that fusion involves a much smaller emphasis is very important, a much smaller volume change than vaporization. This results in a smaller, because there's a much smaller volume change for fusion, it therefore results in a smaller change in intermolecular spacing. Smaller change in intermolecular spacing. Of course, if there's a smaller change in intermolecular spacing, we can predict that there will be a smaller change in internal energy. Smaller change in intermolecular spacing, so a smaller change in internal energy. And of course, if there's a smaller change in internal energy, there's a smaller change in internal energy because of the much smaller change in volume, and of course, there's also negligible. There will be negligible work done by the substance, and negligible because work done is equal to pressure times change in volume, and negligible because there's a much smaller volume change for fusion. There is negligible work done, and negligible work done and negligible work done by the substance during fusion. During fusion, hence the latent heat of fusion is less than the latent heat of vaporization. Remember, the change in internal energy is equal to Q plus W. And Q is going to be equal to either mass times latent of vaporization or mass times latent of fusion. So we have said for fusion, there's a much smaller change in volume, so this is extremely small. And there's a smaller intermolecular spacing, so this is also going to be extremely small. In other words, molecules are not going to move very fast. They will not have a lot of kinetic energy, so the internal energy is also, the change in internal energy is also negligible. So it means because this is small and this is small, it means Q is going to be relatively smaller for fusion. Therefore, the latent state of fusion is going to be a very small value. Similarly, if we were to consider vaporization, there's a relatively larger change in volume for vaporization. The work done is also going to be relatively more because of the greater change in volume. That large intermolecular spacing may result into molecules being able to move freely and faster. That results into higher internal energy, and therefore Q may be larger, which would result into a large value of the latent state of vaporization. State 3 of the basic assumptions of the kinetic theory of gases. So the basic state 3 of the basic assumptions of the kinetic theory of gases. So I may state many of them, just pick out the three. One, we know that molecules are always in a continuous, constant random motion. That's number one. So molecules are in constant random motion. That's number one. Number two, of course, we mentioned that all collisions are perfectly elastic. That's why the molecules were considered to be identical, perfectly elastic spheres. So all collisions between molecules are perfectly elastic. Number three, we mentioned that the intermolecular forces are negligible except during collisions. So we shall say intermolecular forces are negligible except during collisions. Number three, volume of molecules is negligible compared to the volume of the gas. Volume of molecules themselves is negligible compared with the volume of the gas. And many times we consider that the collisions involving the molecules are instantaneous. They occur immediately. They occur instantly. So collisions involving molecules are instantaneous. There is also a large number of molecules, so that an average behavior is always considered, and so on and so forth. You just know and needed 3. And I've given you the most important 4 ones. Explain how molecular movement causes the pressure exerted by a gas. Of course, when a molecule of a gas collides with a wall, it rebounds. It experiences a change in momentum. A change in momentum over time results into a change in momentum is the impulse, and the change in momentum over time results into a force. There are several of such molecules colliding with the walls of a container, resulting into an average force exerted on an area, which is the pressure exerted by the what? By the molecules. So I'll say molecules collide with the wall. Molecules collide with walls of the container and rebound. So momentum of the molecules changes during collision with the wall. So the momentum of a molecule, so the momentum of a molecule changes during collision with walls. Of course, the change in momentum is caused by the force on the molecule by the wall. The change in momentum is caused the change in momentum is caused by the force on the molecule by the wall. So the molecule experiences a force the change in momentum is caused by the force on the molecule by the wall. So the molecule experiences a force from the wall, and by Newton's third law, the molecule also exerts a force on the wall. So the change in momentum is caused by the force on the molecule by the wall by Newton's third law. Newton's third law. The molecule also exerts an equal. The molecule also exerts a force on the wall. The molecule also exerts a force on the wall. Remember, there are many molecules exerting forces across the area of the wall, which leads to the pressure on the wall. There are many molecules exerting force across across the area of the wall, which leads to pressure on the wall. The figure 4.1 shows the variation with the thermodynamic temperature T of the mean square speeds for two gases X and Y. Okay. Then for figure 4.2 shows the variation with the temperature with the T of the product PV for samples of the two gases where P is the pressure of the gas and V is the volume of the gas. State three conclusions about the gases and their samples that may be drawn from the figure and the figure 4.1 and figure 4.2. The conclusions may be qualitative or quantitative. Use the space below for any working that you need. So one thing we need to establish first are some of the important expressions here. Because this was mean square speed against temperature, I will need to have an expression for mean square speed. Remember, PV equals to nRT, which is the same as nKT. Similarly, this equation PV is equal to a third mn mean square speed is given the list of formula. When we combine these two equations, we shall have that 1 over 3 mn mean square speed is equal to nKT. N cancels, multiply both sides by a half. You have a half m mean square speed equals to 3 kt divided by 2. So it means that the mean square speed is going to be equal to 3 kt divided by m. That's number one. So that means if I have a graph of mean square speed against the temperature, the gradient is going to be 3 over 2k, 3k over m. Okay. Then if I want to find the mass, if I want to find the mass of each of the gases would be found from the mass of each of the gases would be found from the mass of a molecule, not the mass of the mass of the mass of each of the molecules. The mass of a molecule would be found from using this equation here. So this could also be 3 kt divided by the mean square speed if I want to find the mass of a molecule. Then what else can I find? If I want to find the number of moles, I can come back here. PV is equal to that. So it means the number of moles is going to be PV divided by RT, which can be found from these graphs. If I want to find the number of molecules, I know that number of molecules using PV is equal to NKT. Number of molecules can be PV divided by KT. So I'm going to employ any of these formulas to have as many points as possible, as many conclusions as possible. Okay. So let's start with the number of moles, because those are easy to find. So number of moles for X is going to be PV over RT. So this is going to be PV for X. PV, I'll just take this. For Y, I will take this for X. So this is for X is 0.9, and for Y it is PV for Y is 2.7. Then I'll also find number of molecules for X, because number of molecules is PV over KT. Okay, so number of moles of X is going to be 0.9. Of course, that is PV, but it is times 10 to the power of 3. Divided by R, we know that R is 8.31 times temperature, which is 400. So this is 0.9 exponent 3 divided by 8.31 times 400. So that is 0.27. Let me divide this space so that I do a lot of calculations here. Then number of moles for Y is going to be 2.7 times 10 to the power of 3 divided by the same thing, 8.31 times 400. So we have 2.7 exponent 3 divided by 8.31 times 400. So that is 0.81. 0.81. And I think there is a relationship here between 0.27 and 0.81. I'll check that later on. Okay, then let's look at the number of molecules. Number of molecules for X is going to be equal to PV divided by KT. I used PV is equal to NKT. So this is again going to be equal to 0.9 times 10 to the power of 3, that is PV, divided by K. We know that K is 1.38 times 10 to the power of minus 23. That is Boltzmann's constant. And this is going to give us 0.9 exponent 3 divided by 1.38 exponent minus 23. I think there is a times temperature here, which temperature is, I'm taking for X 400. So this is times 400. So times, that is 400 times that. So this is giving us 1.6 times 10 to the power of 23 molecules. 1.6 times 10 to the power of 23. Then the number of molecules for Y is going to be 2.7 times 10 to the power of 3 divided by K, which is 1.38 times 10 to the power of minus 23, again times 400, which is, I think 2.7 is 3 times. I may be forced to multiply that by 3. So 2.7 exponent 3 divided by 400 times 1.38 exponent minus 23. That is 4.9. Number of molecules for Y is 4.9 times 10 to the power of 23. Okay, I can check the mass of a molecule for X. Small m is mass of a molecule. So the mass of a single molecule, for X is going to be, I think I derived the formula above there, and it was 3 kT divided by the mean square speed, because they gave us a graph for the mean square speed. So for X is 3 times K, which is 1.38 times 10 to the power of minus 23 times temperature, which is 400, divided by, let me see the corresponding mean, the mean square speed is, I think this is 5 times 10 to the power of 6. So this is going to be over 5 times 10 to the power of 6. So 3 times 400 times 1.38 exponent minus 23 divided by 5 exponent 6. So that is 3.3 times 10 to the power of minus 27. That is kilograms. When I try to find the mass of Y, it is also the same formula. So it is 3 times 1.38 times 10 to the power of minus 23 times the temperature is 400. But then mean square speed is different, I think. For Y, it is here, the 400 is corresponding to this is in the center, in the middle of that box, which is 2.5. So this is going to be divided by 2.5 times 10 to the power of 6. Of course, this is just half of the other one. Without even pressing the calculator, I think this is going to be 6.6 times 10 to the power of minus 27 kilograms. I think I've calculated most of them. Now I can write the answers. One, I can say both gases, of course, are going to be ideal. Why? Because you see that PV is directly proportional to T. That is an ideal gas. Or you see that the mean square speed is directly proportional to the temperature. It is an ideal gas. So both gases are ideal for both. So both gases are ideal. We have seen PV is directly proportional to T. That's because they are straight lines. Mean square speed is directly proportional to T because they are also straight lines. So both gases are ideal. So number 2, I will say mass of molecule. Mass of one molecule of gas X was 3.3. The mass of a molecule of gas Y is that, or I can say mass of one molecule of gas Y is twice the mass of one molecule of gas X. So I'll say it was 2, I can say mass of a molecule of gas X equals to 3.3 times 10 to the power of minus 27 kilograms. The mass of a molecule of gas Y equals to 6.6 times 10 to the power of minus 27 kilograms. Or instead of writing this statement, I can just say the mass of one molecule of gas Y is twice or is double. Mass of one molecule of gas X. So instead of writing these two, I could write this statement here. It means the same thing. Then next, I can now write about the number of moles or the amount so number of moles of gas X equals to 0.27, I think. and number of moles of gas Y equals to 0.81. Or you can say, I don't know whether 0.81 is about 4 times, but let me leave that at that point. I can write about number of molecules. So number of molecules of gas X equals to, we got it as 1.6 times 10 to the power of 23, and the number of molecules of gas Y was 4.9 times 10 to the power of 23. Or you could say sample Y contains, is that 3 times? Let me see, 4.9 divided by 1.6, approximately 3. And 0.81 divided by 0.27, I think it's also approximately 3. So sample Y contains treble or triple the amount of gas, or the number of molecules as sample sample of Y. Let me sample of Y contains treble, that is 3 times the amount of gas or the number of molecules as a sample of X. Let me be very certain about that. Let me check. 4.9 divided by 1.6. That's approximately 3. Then let me check 0.81 divided by 0.27. This is actually 3. So a sample of Y contains treble the amount of gas, that is the number of moles, or the number of molecules as sample of X. Okay, and many more. The figure shows a pendulum consisting of a metal sphere suspended by a thin string as shown here. The sphere undergoes small oscillations about its equilibrium position. The oscillations may be considered to be simple harmonic. The figure shows the variation with the time t of the displacement x of the sphere for its equilibrium position. Okay, this is the graph. On the figure 5.1, draw an arrow from the center of the sphere to represent the direction of the resultant force acting on the sphere when it is in this position. Of course, the force acts towards the center of equilibrium, and of course, the force is going to be a tangent to the arc of the path which the sphere would move when it is allowed to oscillate. So if it is to oscillate, it would oscillate around that path, something like that. It will oscillate in an arc. So because it is going to oscillate in an arc, then the path is going to be a tangent to this arc. It would oscillate in that arc. So it means the path is going to be a tangent in that arc, so it is going to be a line which points to the left but slightly downwards. So I'll draw a line which is a tangent to the thin string, which is perpendicular to the string. I think this is approximately 90 degrees. So it points towards that point. The arrow must be perpendicular to the string and pointing left, down, left to the left, but below the horizontal, something like that. Then the mass of the sample is 0.15 kilograms. State the amplitude of oscillation. So from the graph, let's see the amplitude. I think this is the maximum displacement, and this is also the peak this side. So this is 0.01, 1, 2, 3, 4, 5, 6. I think that is 0.016. So the amplitude is 0.016 in meters. So that is 0.016 in meters. Then determine the angular frequency. So we know that angular frequency omega equals 2 pi divided by the period, which is going to be 2 pi divided by the period from the graph. So I think period is 0.4. Let me check again, 0.1, 0.5. So the period is 0.4. So the period from the graph is 0.40. And when you press your calculator, 2 pi, 2 pi divided by 0.4. That's 15.7, which is approximately 16. 15.7. Of course, this would be radians per second, but this is approximately 16. Then calculate the total energy of the oscillations. Total energy. So total energy is a constant which is given by a half m omega squared times x naught squared. So this is going to be a half times the mass. What is the mass? 0.15. For omega, I will take the original value, which is 2 pi divided by 0.40 squared. Then the amplitude is 0.016. But this is also squared. So I'll check with my calculator again, the whole of that value times 0.016 squared, then times 0.15 divided by 2. So that is okay. Did I square omega? Let me check again. So 2 pi divided by 0.4, and this should be squared, times 0.016 squared times 0.15, that is the mass. Divide this by 2, 4.74 times 10 to the power of minus 3. So I'll just round off this to 4.7 times 10 to the power of minus 3 in joules. Then on the figure, sketch the variation with x of the kinetic energy Ek of the sphere. Of course, when x equals to x naught, whether positive or negative, the kinetic energy goes to 0. At maximum displacement, the speed is 0, so the kinetic energy is 0. So at maximum displacement, that is at 0.1016, this is the point, 0.016 negative, and this one 0.016 positive. Here kinetic energy will be 0. Then when x equals to 0, then kinetic energy is maximum and is equal to the total kinetic energy, which is 4.7. So this is 4 point, each of these boxes 0.2 on the vertical, 4.2, 4.4, 4.6, 4.7 is in the middle of this box. So I'm going to draw a bell-shaped or a dome-shaped curve. So this is going to be the curve. Yeah, you can draw a better curve, better than mine, using a pencil. So this is 4 point, this is at 4.7 times 10 to the power of minus 3. Okay, so your graph should be at negative 0.016 and 0, positive 0.016 and 0. That's these 2 points. And then we have when x is 0, kinetic energy is maximum, which is 4.7 times 10 to the power of minus 3. State Coulomb's law. State Coulomb's law. Of course, we know what Coulomb's law states, and Coulomb's law relates to point charges. So the force between 2 point charges is directly proportional to the product of these charges and inversely proportional to the square of their separation. You should be referring to point charges. So the force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of their separation. Okay, that is Coulomb's law. Figure 6.1 shows an isolated sphere, an isolated hollow conducting sphere that is positively charged. So it's positively charged. On the figure, draw field lines to represent the electric field outside the sphere. So field lines outside, so they should only be outside. I should try my level best to make them uniform and equally spaced. So the field lines are radial, okay, so you have to draw a neat and equally, almost evenly spaced field lines. Field lines originate from positive, so they should be pointing away from the sphere. I always fight with my students to draw very neat field lines using a ruler. So and try to make sure your field lines are really very beautiful and interesting. Figure 6.2 shows the variation of the electric field strength E with distance x from the center of the sphere. So we see that E inside the sphere is 0. So that means when it stops being 0, we are just on the surface. So Determine the radius in centimeters of the sphere. Because we know that E is equal to 0 inside the sphere, so where it stops being 0, it must be the radius, and this is 3.2. I think this is 3.2 centimeters. So the radius is going to be 3.2. Then calculate the charge on the sphere. Calculate the charge on the sphere. So we know that electric field strength is equal to Q over 4 pi epsilon naught times x squared. So on the surface, E is this value here, which is, I think this is 2.2. 2.2 times 10 to the power of 5. So the charge Q is going to be E times 4 pi epsilon naught times x squared. So that is going to be 2.2 times 10 to the power of 5 times 4 pi times epsilon naught, which is 8.85 times 10 to the power of minus 12. Then times x is the radius, which is going to be 3.2 times 10 to the power of minus 2. So from my calculator, 2.2 exponent 5 times times 4 pi, then times 8.85 exponent minus 12 times 3.2 exponent minus 2. So that is 7. What did I calculate? I said 2 point, what is the electric field strength is power 5, making Q the subject. Okay, let me repeat this again. 2.2 exponent 5 times 4 pi times 8.85 exponent minus 12, then times 3.2 exponent minus 2, 7.8. I think this is squared. So I will just again multiply by 3.2 exponent minus 2 to make it squared. So that is 2.51 or 2.5 times 10 to the power of minus 8. Coulombs. Suggest an explanation for the fact that electric field inside the sphere is 0. Electric field inside the sphere is, suggest an explanation for the fact that electric field inside the sphere is 0. Of course, if it wasn't 0 inside the sphere, then it would mean, if the field was not 0, then it would mean that charge would move inside the sphere until the field becomes 0, or until the field becomes 0. But since charge does not move inside the sphere, then it's because the electric field is 0. That's number one. If we would put a test charge inside the sphere, then the sphere, a test charge which is placed inside the sphere would be pulled equal in all directions because the field is radial in all directions. So that means the resultant is 0. Also, the electric field lines go from positive charge to negative charge. And since there are no negative charges inside the sphere, then E must be equal to 0 inside the sphere. So I'll start with the simplest. A test charge placed inside the sphere would be pulled equally in all directions. Therefore, E is equal to 0. A test charge placed inside the sphere is pulled equally in all directions. A test charge placed inside the sphere is pulled equally in all directions. Number 2, alternatively I could say if the field was not 0, then the charge would move until the field is 0. If the field was not 0, then if the field was not 0, then let me say if the field was not 0, the charges would move until the field is 0. Alternatively, the field was not, if the field was not 0, the charges would move until the field is 0. Alternatively, I would say the electric field lines go from positive charge to negative charge. Electric field lines go from positive charge to negative charge. And since there are no, we know that there are no negative charges inside the sphere, and since there are no negative charges inside the sphere, then electric field inside the sphere is 0. Then electric field inside the sphere is 0. Or I would say the positive charge is equally distributed all over or all the way around the sphere, the surface of the sphere. The positive charge is distributed all over or all the way all the way around the surface of the sphere. So this is enough to tell that the resultant of all these charges is zero. So this also is almost the same as the first one. Define the capacitance of a capacitor. Of course, we know that capacitance is equal to Q over V. Because it's a parallel plate capacitor, it is the ratio of the charge on one of the capacitor plates to the potential difference between the two plates. So this is the ratio of charge on one of the capacitor plates, on one of the plates to the potential difference between the plates. An initially uncharged capacitor X of capacitance C is gradually charged so that the final potential difference between its plates is V, and the final charge is Q. On the figure, sketch the variation of charge with the PD for capacitor X as the PD increases from 0 to V. So we know that charge is directly proportional to V. Charge is directly proportional to V according to from C equals to Q over V. Q is equal to C times V, and C is going to be, the gradient is going to be the capacitance. So it means this is going to be a straight line. So I'll just draw a straight line. Capacitance charge is directly proportional to PD. So this is a straight line where the gradient is the capacitance. So I'll just draw a straight line through the origin. Okay, so that is just a straight line through the origin. Use a ruler, draw a beautiful line. Then determine an expression in terms of QV for the work done on the capacitor X. On capacitor X during the charging process. So we know that work done is equal to the area under the graph. So I'll say work done equals to the area under the graph. And this is going to be a half times QV. That's a half times QV, because that is, the area is a triangle, so it's a half times QV. So the answer here is going to be a half Q times V. Another capacitor Y is initially uncharged. Another capacitor is initially uncharged. The fully charged capacitor X in B is now connected to capacitor Y. So the one which was X was initially charged to a PD which was, I think it was charged to a PD V initially. This is X. And so the PD was V, the capacitance was C, total charge Q, total, let it be Q initially. Then now they're in parallel. The capacitance of capacitor Y is 3C. So this is now 3C. The other one was C. So total capacitance, I will quote C total is going to be for capacitors in parallel we add. So total capacitance is C plus 3C, which is equal to 4C. Okay. Then the new charge here, total charge here. So here we have that PdV. Total PD here is just V, which is equal to charge divided by capacitance C. Then total charge remains constant, so total charge Q is still going to be Q. because it is X which is initially charged and then connected across Y, so total charge remains the same. But then total PD, or the PD across both capacitors, is going to be total charge divided by total capacitance, which is going to be Q divided by 4C. Complete the table 7.1 to show expressions in terms of Q, V for the final PDs across the final charge across and the final charges on the two capacitors. Use the space below for any working that you need. Okay, so we have X and Y. So we know that charge on the capacitor of X is going to be, charge on capacitor X is going to be capacitance of X times the PD of X, which is going to be the capacitance of X was C times the PD of X, which is Q, divided by what is the PD of X? Remember, in parallel, the PD is the same for each. So in the second case, this was initial, before. The PD across X was V. This is after. So the PD across X now is Q over 4C. The PD across capacitor Y is also Q over 4C because they're in parallel. So this is going to be times Q over 4C, which is going to be Q divided by 4. Then the PD across, the charge of capacitor Y is going to be Cy times Vy, which is going to be capacitance of Y is 3C times Q divided by 4C, which is going to be 3Q divided by 4. So the final charges here we have Q divided by 4, and here we have 3Q divided by 4. Then the final PD is the same. PD is Q over 4C and Q over 4C because they're in parallel. But we want it in terms of V. So remember initially V was Q over C. So it means Vx is equal to Q over 4C, which is equal to a quarter of V. Then Vy is equal to the same a quarter of V because initially PD was V, which is the same as total charge Q over C. So this is going to be a quarter of V, and this is also a quarter of V. The PD is the same because they're in parallel. State whether the total energy stored in the two capacitors is less than, the same as, or greater than the energy initially stored. Of course, it must be less than because in connecting the first capacitor to the second capacitor, energy is lost as heat in the connecting wires. So it's less than. And of course, the reason is obvious. Some energy is lost as thermal energy. In the connecting wires. Okay. State what is meant by frequency of an alternating voltage. Of course, frequency is the number of complete cycles of the source per unit time. So the number of complete cycles of the source of alternating current per unit time. It is actually the number of cycles per unit time, that is frequency. An alternating current I in a resistor of resistance 680 ohms varies with the time t according to the equation. When I compare this with the general equation, I equals to I naught sine omega t, I is in amperes and t is in seconds. show that the period of the alternating current is 50 milliseconds. So we know that period equals to 2 pi divided by omega. And omega is comparing the two equations, omega equals to 40 pi. So the period is going to be 2 pi divided by 40 pi. So that is 2 divided by 41 over 20, which I think is 0.05 seconds, which is 0.05 divided by 10 to the power of minus 3, which is 50 milliseconds. Then on the figure, sketch the variation of I with the t between t equals to 0 and t equals to 100 milliseconds. So time for one cycle is 100. This is 100. That is, time for one cycle is 50 milliseconds. So we have two cycles here. So half a cycle should be at 25. Half a cycle is there. So when t equals to 0, what is I? Let me check the equation. Sine of 0 is 0. And when t equals to a quarter of a cycle, then I should be maximum. So I should be maximum. The maximum current is 3.5. So a quarter of a cycle, I is going to be equal to I naught, which is 3.5 amperes. So at a quarter cycle, which is 12.5, so we have this point here, this is 3.2.4.5 is here, so this should stop around in the middle of this box. Even here, it should not go beyond this box. 3.5 is in the middle of this box. So we have that point, we have this one in the middle of the box, we have this one. We go to the bottom in the middle of the box, we have this one. We come back in the middle of this box, we have this one. We come back in the middle of this box, and then we come back to 100, that is after 2 cycles. So I will just sketch a smooth curve. You can sketch one which is better. Okay, so this is at 3.5 there, positive. This is at negative 3.5. Determine the root mean square current in the resistor, root mean square current in the resistor. So we know that I root mean square is equal to I naught divided by root of 2. So that is 3.5 divided by root of 2, which is 2.47. That is 2.47. Yeah, I think it's 2.47. 3.5 divided by root of 2. That is 2.47. I know that one. So, or you can write this as 2.5. Use data from B, including your answer in B Roman 3, to show by calculation that the mean power in the 680 ohm resistor is a half the peak power. So we know that power is equal to I squared. That is for DC values or direct current values. So the peak power, P naught, is going to be I naught squared times R. That is the peak current times R. So this is going to be equal to the peak current is 3.5 squared times resistance, which is 680. This gives us 3.5 squared times 680, that is 8330. 8330 watts. That is the peak current. Then the mean current, the mean power is going to be equal to the I root mean squared, then times R, which is going to be, I'll take 2.47 squared times 680. So this is going to be equal to 2.47 squared times 680. That is 4150. 4150 watts. So we are trying to show that the mean power of the 680 resistor is half. So I'm going to divide mean power divided by the peak power is going to be 4150 divided by 8330, which is going to be 4150 divided by 8330, that is 0.498. So this is 0.498, which is approximately 0.5. So the mean power is approximately equal to 0.5 of the peak power, or the mean power is approximately equal to half of the peak power. This one is the peak. When I write P naught, that is the peak. This is peak, and this is mean. Electrons in a vacuum are accelerated from rest through a potential difference V to form a beam. The electrons each have mass m and charge q. The beam is incident on a graphite crystal that acts as a diffraction grating. After passing through the crystal, the beam reaches fluorescent screen. An interference pattern is observed on the screen. Of course, the interference pattern is going to be a diffraction pattern. Explain what this observation shows about the nature of electrons. So diffraction, because we are going to observe interference is going to be as a result of diffraction, and diffraction is a property of waves. So I'll say diffraction is a characteristic. Is a characteristic of wave behavior. Is a characteristic of wave behavior. So this shows that electrons can behave like waves. Or diffraction is a property of waves, so electrons have wave-like behavior. Then determine an expression in terms of m, q, and v for the momentum p of an electron in the beam. An electron in the beam, of course, the electron is going to lose electrical potential energy as it gains kinetic energy, because the beam is incident on the graphite crystal. So I will say loss in electric potential energy is equal to the gain in kinetic energy. So the loss in electric potential energy is going to be Q times V. That is accelerating PD. The gain in kinetic energy is going to be a half. times mass times small v squared. I'm multiplying both sides by m, so I will say m times qv is equal to a half mv squared times m. So I now have mqv equals to a half m squared v squared. And we know that momentum p is equal to mv, but this is squared. So we have mqv is equal to a half times momentum squared. So it means P is going to be equal to 2 times M times Q times V under the square root. So this is going to be square root of 2 M Q V. The PED through which the electrons are accelerated is now increased to a greater value. So V is increased. Describe and explain the effect of this change on the interference pattern observed. So momentum is equal to the square root of twice mqv. So the PD is increased. Increasing V means the momentum has been increased. But we also know that our momentum is equal to h over lambda, or we know that lambda is equal to h over momentum. So increasing the momentum means decreasing the wavelength. We also know that n lambda is equal to d sine theta, because the crystal spacing is acting as a diffraction grating, so n lambda is equal to d sine theta. Because the wavelength decreases, then sine theta decreases. That means the patterns are going to move closer to each other. It's because the angle of diffraction theta has decreased. Since sine theta decreases, since wavelength decreases, sine theta decreases, so theta decreases. So you can say the electrons have greater momentum. The electrons have greater momentum, so smaller de Broglie wavelength, so have a smaller de Broglie wavelength, and the fringes get closer together. And the fringes get closer together. So the fringes are going to be closer, because as V increases, momentum increases. From the equation, momentum is h over lambda, or lambda is h over momentum. If momentum increases, the wavelength decreases. Using the diffraction grating, if the wavelength decreases, then sine of theta decreases, and therefore theta decreases. So it means the fringe patterns are going to be closer because the angle of diffraction is smaller. The electrons are now accelerated through different values of V, resulting in pairs of corresponding values for P and the de Broglie wavelength lambda. On the figure, sketch the value with 1 over lambda. So we know that momentum is equal to h over lambda, or momentum is equal to h times 1 over lambda. So we are plotting P against H of 1 over lambda. We notice that P is directly proportional to 1 over lambda. So this is a straight line, obviously. I know many people will think it is a curve. It would only be a curve if it was P uh, against lambda alone, but because it is 1 over lambda, then it is a straight line. So it is going to be a straight line through the origin. So it is a straight line through the origin because we are plotting P against 1 over lambda. We are not plotting P against lambda. And I'm saying if it was P against lambda, it would not be a straight line. But since it's P against 1 over lambda, and we see that P is directly proportional to 1 over lambda, then that is a straight line. State the name of the quantity represented by the gradient. Of course, from this graph, from P equals to H times 1 over lambda, comparing with Y equals to mx plus C. This is the gradient is Planck's constant or Planck constant. So that is Planck's constant. Okay, I think I have one last question. Radioactive decay is both random and spontaneous. State what is meant by random. Of course, random means we cannot predict which nucleus will decay next in a given sample. So we can not predict. We cannot predict which nucleus will decay next in a sample, in a given sample. Or you can say that a certain nucleus is going to decay, but you can't single it out. You can't predict it. Then state what is meant by spontaneous. Of course, for spontaneous, it is not affected by environmental factors. So decay is not affected by external environmental factors such as temperature. State one piece of evidence for the random nature. How do we see that decay is random? Those we see, of course, fluctuations in the count rate, for example. I think that is the most common ones. We have fluctuations observed in a measured count rate. When you try to measure count rate of decay of a sample and you notice fluctuations, it's because decay is random. Then describe the difference between nuclear fission and nuclear fusion. So for nuclear fission, of course, we know for fission, a large nucleus splits. For fusion, lighter nuclei come together. For fission is normally triggered by a neutron, but fusion is normally under high conditions of high temperature and pressure. Fission is splitting, fusion is coming together. So those are relatively easier. I'll just outline them very fast. So large nuclei undergo fusion, whereas small nuclei undergo large nuclei undergo fission, whereas smaller nuclei undergo fusion. That's number one. Number two, fission involves one nucleus splitting into two or more smaller nuclei. Fission involves one nucleus splitting into two or more smaller nuclei, whereas fusion involves two nuclei coming together or joining. Two nuclei joining together to form one large nucleus. Okay, then maybe I can also add fission is usually initiated because there are 3 marks. I'll need to add more. Fission is normally initiated by absorption of a slow-moving neutron, and fusion is usually initiated by very high temperatures and pressure. So fission is usually initiated or triggered by a neutron, whereas fusion is usually initiated by very high temperature. Okay, explain with reference to the variation of binding energy per nucleon with the nucleon number why the process of nuclear fission and nuclear fusion both result in release of energy. Of course, this relies on the resulting binding energy per nucleon after fusion or fission. If you look at a graph of binding energy per nucleon that is sketched in your class, so this is binding energy per nucleon. I want to write this in full. If you look at a graph of binding energy per nucleon against nucleon number, on this side we have one peak somewhere here, and you notice that values this side, there's only one peak. I don't know whether I've sketched this correctly. I need to edit this again. I'm trying to sketch the usual graph of binding energy per nucleon that you normally sketch in your class. I think that is the graph where you put uranium on the other side. So this side you have an arrow pointing in that direction, that is fusion. And you have an arrow pointing in this direction, that is fission. And in both cases, you see that they are all pointing towards the region where we have high binding energy per nucleon. So I will simply say that both fusion and fission, both fission and fusion involve an increase in binding energy per nucleon. Binding energy per nucleon, of course, since binding energy per nucleon is the greatest for intermediate nucleon numbers. So since binding energy per nucleon is the greatest for intermediate nucleon numbers. So the lighter nuclei on the left-hand side combine to form nuclei of relatively higher binding energy per nucleon, that is fusion. The heavy nucleus, such as uranium, splits to form lighter nuclei which have a higher binding energy per nucleon. So in both cases, whether fusion or fission, there's an increase in binding energy per nucleon, therefore energy is released. So both fission and fusion involve an increase in binding energy. I forgot something here. Increase in binding energy per nucleon, and since binding energy per nucleon is greatest for intermediate nucleon numbers, then energy is released. In both cases. So energy is going to be released in both cases because binding energy is greatest for intermediate values or for intermediate nucleon numbers. I think that should mark the end of paper 4s of October-November 2024. See you in the multiple choice of October-November 2024. Until next time, bye-bye.